Hello, in this video we are going to solve a turbine problem with an emphasis on finding the exergetic efficiency of the turbine. I have drawn the turbine on the TS diagram. State 1 is the inlet state. State 3 is the actual exit state at 220 degrees Celsius. State 2 is the isentropic state. But see, the isentropic efficiency compares the actual output divided by the isentropic output, whereas the exergetic or the second law efficiency compares the actual output between when the turbine operates between state 1 to 3, the actual turbine, divided by the maximum possible output when the turbine operates between the same inlet and exit states. That's also called the reversible work, W dot reversible. So that's our exergetic efficiency. So keeping that in mind, let's go. We have already solved a problem. Let me go to that example first. Test steps and single flow device. Let's say PG model. And we have already solved a problem where we found the isentropic efficiency. So I suggest that you go over this solution first. Everything is same in this particular problem, except you are asked to find the exergetic efficiency. So to jumpstart the solution, why repeat everything we have done there? I'll go to the test codes and pick up. These are the test code that came out. Control A, Control C, and let's go launch the app, I/O panel, paste the test code, and load. So that's essentially recreates the solution that we did in the previous problem, and you can see that the isentropic efficiency of 75.6 is already recalculated. So what's the difference here? Obviously, this solution doesn't include exergy at all, so we click this include exergy button, and notice that the new variables such as you can see phi and psi, they show up when we click the include exergy button. Well, the difference now is that to calculate these exergies, we got to go declare what is known as the dead state. State 0 is the designated dead state in test, and the pressure of atmosphere and the temperature of the atmosphere, 25 degrees Celsius, has been supplied. So the idea is that creates that will create the dead state for which the phi and psi are obviously 0. There is no exergy in a dead state. Notice that state 1, if you now go back, exergies have been already updated because now that the dead state is known, for state 2, state 3, everywhere we have the dead states, the exergies calculated. So therefore now we can go to the I/O panel with, also in the device panel, if we go to the device panel, you'll notice we have, we got to go to the device 2 where state 1 is the inlet state and state 3 is the exit state. Notice that the device schematic has been updated for exergy analysis. The heat transfer Q dot is now divided into two different reservoirs. The work output is divided between the useful work and the atmospheric work. Obviously, for a steady device, there is no atmospheric work, which happens for a closed system most of the time. And the heat transfer also, in this case, is adiabatic, so it's 0. So there is no need to mess with the two different reservoirs. So we just click the calculate button. It should calculate the useful work. The atmospheric heat transfer we got to enter with 0 in this case. So therefore, now that we calculate, we will find the reversible work. W dot reversible 2 has been calculated as all the other exergy related quantity. So the reversible work being known now, we can go to the I/O panel and find the exergetic efficiency. Suppose we call it eta exergy. So that will be W dot ext 2 is our useful device, and W dot reversible 1 is that, or Yeah, we are doing the analysis for 2. So therefore the eta exergy is found to be 81.7%. So what we have done here, this is the actual output of device 2. Remember, device 2 is our actual turbine. Device 1 was our isentropic turbine for the previous problem. So in this particular solution, we have found both the isentropic efficiency and exergetic efficiency. This is kind of a continuation of the previous problem. So once again, when you go to the device panel, you will see that when you include exergy in your solution, heat transfer is divided into 2 reservoirs. One is atmospheric reservoir and one is a reservoir at a different temperature. And the atmospheric reservoir, of course, there is no heat transfer in this case. So Q dot is the net heat transfer, and Q dot atmosphere is the heat transfer with the atmosphere, which I set to 0, which results in finding every other quantity. The most important one being for instance, the psi dot. So you can see that it calculates the exergy, the net exergy that goes through the system, and then the reversible work is calculated right from there. And the exergy equations, exergy related equations are shown here. So this is the reversible work, reversible power, which is calculated from Q dot is 0 here, from essentially the flow of exergy through the turbine.